Okay guys, 14.2 is about how we can do double integrals to do volume. If we imagine them from a Riemann sum perspective, normally Riemann sum made rectangles that were one-dimensional looking on our paper, well, two-dimensional, but now the Riemann sums can kind of be three-dimensionals, where instead of being like the width or the height for the Riemann sum, delta x, it's now the area of a prism that's getting shrunk over and over to make a more accurate sketch. The definition of a double integral: if f is defined on a closed and bounded region R in the xy plane, the double integral of f over R is the limit as delta goes to 0 of f of x of I equals 1 to n, the index f of xi, yi, delta ai, provided it exists. So basically we're taking a Riemann sum of two integrals size-wise. Some of the properties we have is you can take functions out of double integrals. If you have addition or subtraction, they can be separated. The area should be positive if the function is positive. The volume. If a function is larger than a second function, then its volume should be larger than the second function's volume. And then if you split your region into two pieces, the volume of the first one and the sum of the split regions should be the same. So the same general rules we had previously in 2 dimensions. Fubini's theorem: let f be continuous on a plane region R if R is defined by a function where x is bounded by a and b and y is bounded by g1 of x and g2 of x, where g1 and g2 are continuous on a and b, then the integral, or the double integral over R of f of x, y, dA is the integral of g1 x to g2x of the function, first with respect to y, and then that integral is integrated from a to b with respect to x. Similarly, if you instead define it by y and then x as a function of y, then you would do dx first and dy second. And what does that mean? It means if you can find a cross-section of the shape for y or x in terms of the other, then you can double integrate. Let's say you're finding the volume of the 3D shape to the right, for example, this prism. It has the given lines for the shape. The volume should be the area of the base integrated from 0 to 2, but the base depends on 2 dimensions. What if you could generate the base by first integrating the base relationship based on a single variable? You can actually use the cross-section to generate a double integral. So the volume over the reals really is from 0 to 2 for the height, but before that, if we look at the cross-section, which is kind of this side picture of what this looks like, we know that there's a relationship between the height and x and y. That height, z, is equal to 2 minus x minus 2y because of the way that our triangle prism is shaped. These are arguably easier to do if someone simply gives you the integral to solve, then it's not so bad. Sometimes looking at the picture and setting it up yourself is a little bit harder. So let's look at what that will look like if we're just evaluating first. So evaluate the double integral of 1 minus 1/2 x squared minus 1/2 y squared dA, where R is bounded by x is between 0 and 1, and y is between 0 and 1. The order here probably should not matter, as x and y are identical and they're both bounded by a constant, not a function. So let's go ahead and do y first. So we have 1 minus 1/2 x squared minus 1/2 y squared dy dx. So if you integrate with respect to y first, we get the integral from 0 to 1 of y minus 1/2 x squared y minus 1/6 y cubed, evaluated from 0 to 1, dx. When we plug in 1 for y, we get 1 minus 1/2 x squared, looks like minus 1/6 dy or dx. Integrating that with respect to x, 1 minus 1/6 is 5/6, so we'll get 5/6x minus 1/6x cubed, evaluated from 0 to 1. When we plug in 1, we just get 5/6 minus 1/6, which is 4/6 or 2/3. So that's the area of the shape. Another thing this can be used to do is to find the average value of a function over a region. So if f is integrable over the plane region R, then the average value of f over R is 1 over a times the integral of f of xy. So basically you take the total area or total volume and divide it by the area. An area is just the width of x times the height of y, the area of the region. So it says find the average value of the function f of xy equals 1/2 xy over the region R, such that x is between 0 and 4 and y is between 0 and 3. That means the width, area is length times width. The length here is 4 because it's from 0 to 4, the width or the height, 0 to 3, so the area is 12. That means our integral should be 1/12 times the double integral. We'll do x first this time. So y goes from 0 to 3, x goes from 0 to 4, 1/2 xy dx dy. Pull the 1/2 out, so this is 1/24 times the integral from 0 to 3. So this integral with respect to of xy would be 1/2 x squared y, evaluated from 0 to 4. Still dy on the outside. So this is 1/24. When I plug in 4 for x, I get 16, so this should be 8y. We can pull the 8 out if we want. 8/24 is 1/3. This is 1/3 times the integral from 0 to 3 of y dy. The integral of this is y squared over 2, so this is 1/6 times y squared, evaluated from 0 to 3, which should just be 1/6 times 9, or 9/6, which is 3/2. So because that means the volume roughly is probably 18 divided by 12, 3/2. If we hadn't, so we got 9 here because we pulled a half out. It would have been 1/2 without the 1/2 being pulled out beforehand. And that is all 14.2.